In our previous lecture, we were looking at the bonding forces between molecules in liquids, called the intermolecular forces, because in liquids things are existing as molecules. We talked about the three major categories: hydrogen bonding, which of course is rather selective because it involves only compounds that have hydrogen, which is attached to oxygen, nitrogen, or fluorine. We have dipole-dipole forces, which exist in molecules that are permanently polar. And then we have London or dispersion forces, which exist in all types of matter, in other words, in all types of molecular liquids. One of the physical properties associated with liquids is what we call their vapor pressure. And vapor pressure is one of the properties which is dependent upon then these intermolecular forces. We talked just a little bit about how vapor pressure arises yesterday as we took a look at this drawing, and we indicated that if we started out with a container and placed some liquid in it, as we see in the first drawing here, we would notice that we had zero as far as the pressure gauge. However, after some time, we would note that a pressure does exist, meaning that some of the molecules have escaped from the liquid and are in the gaseous phase in order to exert pressure in the container. The process of the molecules escaping from the liquid into the gaseous phase is referred to as evaporation. But there is also a reverse process that can occur. After we have some molecules in the gaseous phase, some of them might strike the liquid surface and re-stick, go back into the liquid state, and we refer to that process as condensation. We said that after some time, the pressure gauge will remain a constant, meaning then that the rate of evaporation has become equal to the rate of condensation. In other words, the kinetic motion of the molecules is still continuing on, but at a rate then in such that the rate at which molecules leave the liquid now becomes equal to the rate at which they return. And when we reach that particular condition, we referred to that as the vapor equilibrium vapor pressure of the liquid. Now, the equilibrium, of course, that means because we have two opposite processes going on in equal magnitude. Vapor pressure is the pressure exerted by the gaseous molecules. The equilibrium vapor pressure of a liquid is temperature dependent. And so, in other words, it's not the same at all temperatures. So if we look at, again, the effect of temperature on vapor pressure for a particular substance, we find that as temperature increases, vapor pressure likewise increases. What this graph was pointing out, that in fact the change in vapor pressure is not a linear, so we'll put an X through that. It's not a linear relationship, it's an exponential relationship. So as temperature goes up, it starts out changing very slowly, but then vapor pressure begins to rise very rapidly. And we can further state that the vapor pressure of a liquid is directly proportional to temperature. So in other words, there is a direct relationship between the two. And of course, the vapor pressure, then how easily molecules can escape from the liquid, goes back to these intermolecular forces: hydrogen bonding, dipole-dipole, and London dispersion forces. Now, one other thing that we can say, well, let me come back to that in just a second. Let's take a look at four representative compounds here and look at their vapor pressure. This would be the vapor pressure at a particular temperature, and I believe the temperature here is, if I recall, 20 Celsius degrees. Notice that this is the molar mass. If we were to look at water, which has very little mass to the molecules, one would predict or at least suspect that water molecules could escape very easily, and if that were true, then water should have a very high vapor pressure. But notice that even though it is the lightest molecule, it has the lowest vapor pressure of the four liquids given. Now, the reason for that is that when we look at water, remember we said that water has hydrogen bonding. So if we talk about water, we have hydrogen bonding possible. And of course, it is a polar molecule, so it also has dipole-dipole interaction, and everything has London forces. So the bonding forces in water molecules is very high, very strong intermolecular force. Therefore, water molecules cannot escape very easily. Okay? So we have a very low vapor pressure for water as compared to its mass. Now, we would suspect that the heaviest molecule, carbon tetrachloride, would be the hardest for molecules to escape because they're bigger, they're heavier, more mass, matter attraction. But again, we see that's not the case. It's not the highest, it's not the lowest vapor pressure. Water is lower. Even methanol, which is about 5 times smaller in mass, has a vapor pressure about the same. Well, if we look at carbon tetrachloride, what we found when we looked at it as far as geometry, etc., it's a tetrahedral molecule. It's nonpolar, so it doesn't have any dipole-dipole forces. It obviously can't have any hydrogen bonding because there's no hydrogen in it. And so the only force that exists in the carbon tetrachloride then are the London forces. And that's the reason that even though it has a very high mass, it has a relatively high vapor pressure. It's still pretty easy for carbon tetrachloride molecules to escape. Okay? Also, carbon tetrachloride is rather compact. And compact molecules have lower dispersion forces than spread out type of molecules. Notice the pentane here, even though it's only half as heavy, has a much higher vapor pressure. Again, no hydrogen bonding involved in it, etc. So we see that to know or predict something about vapor pressure of a substance, we need to know something about the intermolecular forces. And that's where it comes in and looking at the geometry, looking at hydrogen bonding, looking at polarity, all comes into predicting what type of vapor pressure one would have. All right? Now, if we go back to our vapor pressure chart for just a second, we had here, and let's suppose that this point right here represented 760 torr. This temperature then, if we go over here, this temperature down here corresponding to that is referred to as the normal boiling point. Now, what do we mean, first of all, by boiling? What is boiling? Boiling is the rapid evolution of the vapor or gaseous state from a liquid. That's what boiling is. When we see water boil, it's the rapid evolution. The bubbles are full of gaseous water molecules. That's what the bubbles are that we see rising. So the rapid evolution of the gaseous phase from the liquid is referred to as boiling. Normal boiling is, or normal boiling point, is the temperature at which a liquid boils when its equilibrium vapor pressure equals 1 atmosphere or 760 torr. But a material will boil, a liquid can boil at nearly any temperature because boiling is dependent upon the applied pressure. Anytime that the equilibrium vapor pressure, and we'll just call it vapor pressure, anytime the vapor pressure is equal to the applied pressure, boiling occurs. So therefore, if we lower the applied pressure, notice if I were to come down this graph, and let's say that I were to apply a pressure down here, now about a fifth of what we had, so we'll say 150 torr approximately. If I apply a pressure of 150 torr to this liquid, it's going to boil way down here. That would be its boiling point at the pressure that we are applying. So boiling, when we talk about boiling, boiling is a phenomenon related to the applied pressure. If we want to force something to boil at a higher temperature than normal, than its normal boiling point, we can increase the applied pressure. Has anyone here ever cooked using a pressure cooker or pressure cooker pan? No one has. All right? Well, we can use a pressure cooker to do exactly that, to apply a greater pressure, a pressure greater than 760 torr, so that we can actually force the water to become warmer than 100 Celsius degrees before it boils. If we can do that, if we can get the water to 120 degrees before it begins boiling, obviously then we can cook foods quicker. And this is the purpose then of using a pressure cooker. As a matter of fact, if you lived at a high elevation, if you were to try to cook something, let's say on Pikes Peak, you went camping, you went hiking, and you stayed out on Pikes Peak, and you wanted to cook something, and you remembered that, well, to cook a potato, it should take about 45 minutes in boiling water, and so you put up your fire, your campfire, and you put the pan on, fill it with water, throw the potatoes in, boil it like mad, and pour the water off and cut the potato in 45 minutes. It's just as solid as can be. It's hot. It's probably be about 95 Celsius degrees, but it's not cooked. Because the conversion of the starch in a potato requires a temperature of about 98 Celsius degrees. Water boils at about 95 or 94 degrees on top of Pikes Peak. You can't convert the starch. You don't have a temperature necessary to carry out the chemical change. And your food would basically be hot but still raw. If you were going to do a boiled egg and you threw the eggs in and cooked it for 5 minutes and you broke them open, you would have nothing but a hot, uncooked egg, raw egg, because the white part of the egg takes a temperature, again, very near to 98 Celsius degrees to undergo the chemical change that gives us the cooked appearance to an egg. So people living at higher elevations often have to use a pressure cooker in order to carry out the cooking process, to get the water up to at least 100 degrees so that the cooking can occur. Again, boiling is going to occur any time that we reach that set of conditions where the vapor pressure and the applied pressure have become equal. Boiling is going to occur. As a matter of fact, we can, by reducing the pressure, we can actually get water solutions to boil at very low temperatures. If you talk about instant coffee, it's often called freeze-dried. Freeze-dried instant coffee. When instant coffee was first produced, the way they would make it was basically brew up a pot of coffee, pour it into a pan, set it on a stove or something hot, and evaporate the water off. Well, what that left you then was coffee, solid coffee particles, the dissolved materials, then that were in there, and you grind it up and you would put it back into hot water and have a cup of coffee. But the coffee that you got from the first instant coffees tasted about like the coffee does after it has been in a pot all day long and plugged in. Nice hot. Anyone that is a coffee drinker knows what I'm talking about. The coffee after 12 hours of sitting in a coffee pot is not the same flavor as the coffee that was brewed initially, because the temperature causes many of the flavoring chemicals to undergo a change, which gives it a totally different flavor. And the early instant coffees did not taste like fresh brewed coffee. Freeze-dried coffee, now what they do now is they make the pot of coffee up, quickly begin cooling it, and then as they cool it, they also reduce the applied pressure. And as they reduce the applied pressure, the coffee continues to boil, meaning that the liquid water is escaping rapidly, until finally we get it to the point that water is actually escaping as it freezes. And as it freezes and still loses the water because we have very little pressure above it, what we end up with now are crystals which haven't undergone this constant heating process. And therefore, when we reconstitute it by adding hot water, we do get a cup of coffee that tastes closer to fresh brewed coffee. There is still some change has occurred. So we can use this principle here. Then by changing the applied pressure, we can change what temperature a material boils at. Okay? Now, if we were to look at what happens as we heat, okay, once again, boiling, when vapor pressure liquid equals applied pressure. If we were to look at what happens to temperature as we begin heating a liquid, we would see something that looks like this. We would see that as we began to heat the liquid, the temperature would rise. For instance, if we put a glass of water, a cup of water into a pan and measured its initial temperature might be about 20 Celsius degrees, room temperature. And we turn on the stove, we turn on the flame, and what happens is the water temperature begins to rise. But then finally we reach the point that it begins to boil, the phase change, as it goes from a liquid to a gas, evaporation. And once we reach the boiling point, all of the energy that goes in from here on out goes into the phase change. Notice there is no longer a temperature change as we reach the phase change. All of the energy going in is now being used to convert liquid to gas. And the temperature would remain a constant until we finally had converted all of the liquid to gas. Then we could actually begin heating the gas itself. Now, this just points out one thing. If I'm cooking, then the most efficient energy-wise for cooking would be to get the water just to its boiling point and just barely maintain minimum boiling. Because cranking up the heat isn't going to do anything to raise the temperature. We're at the highest temperature we can get. All we're going to do is boil the water off faster, dry the pan out and burn the food in the pan while we're not paying attention. All right? So once you get it boiling, you might as well conserve on energy. Cut it down as low as you can to just maintain the boiling, because the temperature is going to remain a constant until all of the liquid has evaporated. All right? Now, the amount of energy needed to change, then, 1 mole of substance from its liquid to gaseous state at its boiling point is referred to as the molar heat of vaporization. The molar heat of vaporization is the energy needed to change 1 mole of liquid to gas at its boiling point. In other words, this doesn't involve any of the heating, just merely the phase change part. The reverse process is molar heat of condensation. However, we usually use only one table. We call it the same thing regardless of which direction we're going. However, one way energy is being put in. So when we're vaporizing something, we're putting energy in. That's endothermic. We talked about that before. And if it's condensing, energy must be given off. And that's an exothermic process. But the magnitude, the amount of energy, is the same. Whether we're evaporating or condensing, we're going to have the same amount of energy changed per 1 mole of substance. Now, the molar heat of vaporization sort of corresponds again to these intermolecular forces. The stronger the forces, the more difficult it is to tear it apart into the gas, and therefore the higher the energy requirement. Again, if we take a look at some tabular values here, we have some molar heat of vaporization for 3 liquids here: ethanol or ethyl alcohol, ammonia, and water. And notice that even though water is the one of the smallest mass-wise of the molecules here, it has the highest. It has the highest molar heat of vaporization. To change 18 grams of water, that's about 18 milliliters, to convert 18 milliliters of water from a liquid to a gas at 100 Celsius degrees, we've already heated it there, it will require 40.7 kilojoules of energy. 18 grams of water would require 40.7 kilojoules of energy to change it from liquid to gas. Okay? And kilo, of course, means 1,000, so that's 40.7 thousand joules of energy in the process. All right? Molar heat of vaporization. And by the reverse process, when a mole of water, 18 grams of water, goes from steam, from gaseous water, back to liquid, it releases 40.7 kilojoules of energy. This is why water is used as a heat transfer system. It's very effective. It carries a lot of heat. For instance, this building in the cold time of the year is heated by transporting gaseous water, which we call steam, from a power plant that is producing it. We have boilers that are converting the water to steam. The steam comes through a set of pipes to the building, and in the building it then goes through coils where it condenses back to liquid water. And every 18 grams of steam that comes over to the building is going to give off 40.7 kilojoules of energy as it goes back to the liquid. We take the hot water, run it back through the pipe to the boiler, and reheat it, convert it to steam, run the steam, and we can do this for an infinite length of time. Also, this is why a steam burn is so severe in contrast to just a hot water burn. For instance, the amount of energy to change 1 gram of water 1 Celsius degree is 4.814 joules. Okay? That's the amount of, that's joules, not kilojoules. So for 18 grams of water to change 1 degree, in other words, if I put some hot water on my skin and it changed from 100 to 99, then I would have 18 times this, or we'll just call it about 90 joules of energy. But if I have 18 grams of steam that hits my skin and condenses, even without changing temperature, I am going to release 40,700 joules of energy. That's a lot of heat energy. That's why steam is so severe in terms of a burn. Tremendous amount of heat of condensation or heat of vaporization. All right? Well, we can use these, of course, to do some quantitative calculations, and let's just do one here quickly. let's calculate the number of kilojoules of energy that would be needed to vaporize 100 grams of ammonia at its normal boiling point. In other words, it's already at the boiling point. Now we're going to do the phase change part. And in order to calculate it, the term that we often use, or the letter, is Q. Q stands for heat energy. And so often we'll see it just written as Q. Q will be equal to 100 grams of ammonia multiplied by then the amount of energy, the molar heat of vaporization for ammonia, which was 23.5 kilojoules per mole. But we can see that my units don't work out right there, because obviously grams, it cannot cancel moles, so we need to bring in one other factor. That is, we have to convert this from grams to moles. So we can multiply by 1 mole of ammonia over its mass, which would be 14 plus 3, so that would be 17.04 grams. And so now the grams of ammonia cancel, the moles of ammonia cancel, and we're left with units of kilojoules. Well, let's see. We would have 100 divided by 17.04 and multiplied by 23.5. We would have 137.9 kilojoules of energy to convert 100 grams to its vapor, or vice versa. If 100 grams of ammonia condensed, we would get that amount of energy released. Ammonia is used as a refrigerant. We talked a little bit about this when we talked about the halogenated hydrocarbons, the freons which replaced ammonia as refrigerants. But both are good refrigerants because they're relatively easily liquefied and vaporize, and both of them have fairly high molar heats of vaporization. For instance, if I do have ammonia as my refrigerant, then as it moves through the refrigerator, first of all it goes into a compressor, and in the compressor we liquefy it. And for every 100 grams of ammonia that we liquefied, we'd give off 137.9 kilojoules of energy. If you've ever felt on the back side of the refrigerator or a freezer or an air conditioner, it's very warm. The reason it's warm is we're squeezing that heat out of the refrigerant. As we re-liquefy it, that energy, that molar heat of vaporization, has to be released. Now we have the ammonia as a liquid. What do? We let the liquid ammonia now, which is under pressure, up through some coils in the refrigerator, and as it moves into the coils where the pressure is less, it does what? Goes from a liquid back to a gas. Now, in order to go from a liquid to a gas, what does it have to do? It has to gain 137.9 kilojoules of energy for every 100 grams of ammonia. That goes back to the gas. Where is it going to get that heat? From the food that I put in the refrigerator. When it gets back and circulates back, it's now a gas. It goes back to the compressor. We just squeeze it again. And when we squeeze it and put it back to a liquid, it gives the energy off. And this goes through and through and through. A heat pump does a reverse process. We do the squeezing so that the heat energy is released inside, and we take the energy. In other words, the coil now is outside, and we extract heat from either water from the ground or the air. And we then have the gas, or the ammonia, being converted to a gas outside, and we are compressing it and releasing the heat to the inside. So actually a heat pump is nothing more than a refrigerator hooked up in reverse order. So instead of the heat being the waste material, it's now the positive part. All right? Okay. Well, another property of liquids is a property that we call viscosity. Viscosity is the resistance to flow. So if something is viscous, if it's highly viscous, it means that it has a high resistance to flow. We say something about being slower than molasses in January. All right, well, molasses itself is very viscous. If you try to pour molasses out of a bottle, even at room temperature, it's pretty slow. Okay, it doesn't flow very readily. It has a resistance to flow. And if we cool it down, that resistance to flow becomes even greater. Typically, this is exactly what we find for all things, that viscosity increases as temperature decreases, so that it flows with less ability at a lower temperature. That's why we're saying slower than molasses in January, because if you went out on a cold January morning and tried to pour molasses out of a jar, it just doesn't flow. All right? Now, that's a problem when we talk about lubricating in automobile engines, because what we would like is we would like to have a lubricant that was rather viscous when the engine was hot to prevent wear. But yet, viscosity of things decreases as things get hot. So when we put oil in an automobile, for instance, first of all, if the engine is cold, the oil is fairly viscous, it's fairly thick. And as the engine warms up, the oil becomes less viscous, it becomes more runny, and it doesn't lubricate as well. And so that's a problem. Well, in the early days of oil, we would have things like this. We would have an oil, we sometimes call it a weight. It's also referred to as an SAE number. That's the Society of Automotive Engineers, are the ones that have calibrated these, SAE. If you had an oil that said HD30, that means that it has a certain viscosity at room temperature, at normal temperature. All right, but that viscosity changes as the energy or the temperature in the engine changes. Now, if you lived in a very cold country, this becomes a problem. If I use 30 weight, that means it's a little viscous, that means it lubricates the engine well, but on a very cold morning, that oil is going to be so viscous it's going to be very difficult to turn the car engine over. We've got a lot of drag now, and it's difficult to get the car engine to even turn over. So people that lived in northern climates early in the automobile history would use then something like oil of 30 or 40 in the summer when it was hot, and then comes winter, they would drain it all out and put in an oil that was like what we call a 5 or a 10. Now, a 5 or a 10 means that at cold temperatures, it's still fairly runny. At high temperatures, it becomes very runny. But if you were in a cold climate, you probably didn't worry as much about the car lubrication on the warm end as you did being able to start it on a morning when it was 40 below zero. And so you would use an oil that was like a 10 or a 5 weight oil. So you changed twice a year. Changed going into winter, changed going into summer. Summer to give you better lubricant, winter to give you easier starting, less drag on the engine. Well, we can see here 3 oils that show a variable number. The first one there says 10-30. Because I can't get that real clear. Next one, 10-40, and another one over here, 20-50. Now, we talked about polymers, polymerization in Chapter 7. Chemists have figured out ways that we can add certain chemical additives that begin to polymerize as temperature goes up. Now, that means that we take small molecules sitting in the oil, and when it's cold, they're as individual molecules. As it gets warm, these individual unsaturated molecules begin to polymerize. They begin to hook together. And when they hook together and make bigger molecules, the viscosity increases. And so what this number implies here is that when this oil is cold, it will have a viscosity of about 10. meaning the engine has an easy start because the oil is not very viscous. As the engine temperature increases, the oil viscosity actually increases to 30, where normally the oil viscosity would decrease. The oil viscosity now is increasing. And so at high temperatures we get the same lubricating that we would with a 30-weight oil, but when it's cold we have the less viscous, easy starting property of the oil at a 10-weight oil. So instead of needing to change oil twice a year and putting in a 10 in the winter and a 40 in the summer, we can use a mixed oil, a variable weight oil, to handle the entire year round. So viscosity is resistance to flow, and in the case of the oils, of course, it can be adjusted by adding particular chemicals, and most of the oils we see today on the market are actually a variable weight. Occasionally you still would want to use, if you were using, say, a lawnmower, you normally aren't going to mow in the winter time. And so you don't worry too much about the starting part, because you're going to basically do it in warm weather anyway. And if that's the case, then you would use an oil that gives you more of a constant lubrication, which would be something like a 30 or a 40 weight oil. So there are still times when we want to use just single type of viscosity oils. But for automobiles today, most of it is in form of the variable. Now, one other property of liquids occurs at the top of the liquid. Let me just say this here. I'll say viscosity is what we call a bulk property. By that we mean that the viscosity is the same through the entire thing. The other phenomena we're going to talk about is called surface tension. And surface tension is then a special property of liquids that occurs only near the surface of the liquid. If we were to look at a layer of liquid, the molecules sitting up here, for instance, do not have anything to attract them upward. If we took a molecule here, it's attracted to molecules in all directions. The molecules up here cannot be attracted to anything above, and so basically their only attraction are for things down this direction. Now what that does then is it compresses this top layer. So this top layer then becomes more dense than the bulk of the liquid. So there's a compression factor in the top layers, top rows of the liquid. As a matter of fact, this compressed layer, this more dense layer, can actually become quite dense. In the case of water, which has hydrogen bonding, polar bonds, etc., very strong intermolecular forces, the surface tension on water is quite strong. It's the surface tension of water, for instance, that accounts for water beating up when we put it onto a waxed surface. The water molecules like themselves so well that on the surface they begin attracting inward and they just pull into a drop shape. So they beat up. All right? The strength of this, as I said, can be relatively great. If we look at insects, aquatic type insects like mosquitoes, for instance, and we notice they can stand on water. Notice here, if you can see this, where the legs are. Let me slide this over a little bit. See where the legs are here, setting on the water, how it is actually caved in somewhat. It's just like taking a piece of paper. This film on top of the water is sitting there, and where the leg is, it's compressing it a little bit, but it's not breaking through. The density of that top layer of water is dense enough to support the mass of the insect on top of it. Now, if you were to take that mosquito and put it down in the water, it would sink because its density is greater. But its density is not greater than the density of the surface tension itself. That surface tension may be several hundred times greater than the bulk density of the solution. One is actually able to support a piece of iron. Iron has a density of 4 or 5 grams per cubic centimeter. Water is 1, so it's 5 times more dense than water. And you can actually put a piece of steel on top of a piece of water and it won't sink if you're careful not to break the surface tension. Now we can break the surface tension. We can destroy that interaction of the water molecules if we put in another type of molecule that will interfere with water attracting water. These are referred to as surfactants, or we call them soaps. The reason we use a soap partly is to break down this beading effect. If you ever put see water on a soapy surface, it spreads out instead of beads up. The reason it spreads out is because the soap molecules interfere with the water-water molecule interaction and weaken the surface tension so that it tends to just spread out instead of bead up. If we were to put some soap in water, the insect would sink because we have destroyed the surface tension layer. As a matter of fact, that's one of the ways that especially mosquitoes, are controlled in areas where we don't want to use pesticides, but we don't want them to be able to hatch, and we still have small ponds of water or whatever. We can add a surfactant. When mosquitoes, as larvae, they're in the water, and they undergo their change, they literally crawl out on top of the surface tension and dry off. And a mosquito has to dry off so that finally its wings will be able to work and it can fly off someplace and look for a meal. And if we disrupt this surface tension layer, it can't get on the surface and it will drown. It'll undergo its change, but it would never be able to escape the water, and it would die of starvation or not being able to get air either way. And so we can kill or control the insect. So using soap or surfactant materials is one of the ways that we can help control the mosquito population. And as I say, in areas that we don't want to use pesticides, where we might have small ponds of standing water that insect hatching could occur, this is one way to control it. All right. Well, just about out of time here, but let's go ahead and mention just quickly here. In our next lecture, we're going to spend additional time looking at solids and some of the intermolecular forces there. And we're going to look at 4 different types of solids. We're going to look at molecular solids, ionic solids, metallic solids, and covalent solids. And we'll look at some of the property differences, what accounts for the differences of these 4 types then of solids. But we can go on here quickly because this relates so closely to what we've talked about in liquids, and that is the molecular solids. The molecular solids, because again we're talking about molecules as units here, behave just like liquids. So any of the forces we talked about in liquids are also the forces that we talk about in the solids. In other words, if we talk about water in a solid state, we're going to have the same forces involved that we had in water in the liquid state. We're going to have hydrogen bonding, we're going to have dipole-dipole, we're going to have London forces. If we talked about solid carbon tetrachloride, we're going to talk about a nonpolar molecule, no hydrogen bonding. The only forces would be the London forces. Okay? So molecular solids have the same interparticle forces as liquids. Same type of forces. And here we see then 4 different solids here. Can't seem to find a average focus here. But we have iodine, carbon dioxide, water, and sucrose. This is sugar molecule down here, table sugar. The number on the left-hand side represents the molar mass. Again, we have water, 18, carbon dioxide, 44, sugar, 342, and the iodine molecule, 254. But this one, iodine, strictly nonpolar, no hydrogen, so the only thing it can have is London forces. Carbon dioxide as a solid. Carbon dioxide as a solid, of course, is what we call dry ice. Again, it's a nonpolar molecule, and this is part of the purpose of drawing Lewis structures and geometric shapes. It's a nonpolar molecule. Water, polar molecule, hydrogen bonding, and of course this one has hydrogens attached to oxygens. If we drew out, I didn't try to draw out the structure for this, but if we did, we'd have a lot of hydrogen bonds, and so we have, again, strong forces there. Now, these two particular materials, and especially this one, undergo a process which is called sublimation. Sublimation is the direct phase change from solid to a gas with no liquid state. Now, most things go from solid, and if we heat them up, they go to a liquid. If we heat them up, they finally go to a gas. But there are some materials that have the ability to go directly from the solid state to the gaseous state. And this is called sublimation. Carbon dioxide goes directly from a solid to a gas. That's why it's called dry ice. Solid carbon dioxide looks a lot like ice, looks like a cloudy looking ice. Ice in terms of being frozen water. But in the case of water, if we're going to use it as a refrigerant, it's going to go from solid state, it would melt, and then it would be a liquid. And of course, obviously, if you're trying to pack things with this, you've got water against cardboard or paper, and it's soggy, and the boxes fall apart. Not good. But if we use dry ice, as the carbon dioxide absorbs heat from the food, keeping it frozen, it goes directly to a gas with no liquid state. And so our packing materials, our cardboard boxes, the paper, the wrapping that we have things in, aren't affected because there's never a liquid state that causes then this type of destruction of the wrapping material. So it looks like ice, but it's called dry ice because it never has a liquid state. So carbon dioxide or dry ice is used very extensively, of course, for packing material for cold foods, shipping ice cream, shipping frozen products across the country, whatever, dry ice is used for that material. Sublimation then, okay? All right. Tomorrow then we will take a further look at solids and look at some of the energy changes involved in them as well.